ask everybody, all the panelists and the speakers to come up, and then I'll ask the panelists to introduce themselves, and then we'll get in. We got almost 35 minutes or so to, plus my session's in here next, so if we go over, it's on me, so hopefully the people next, my next session won't be too throwing arrows at me, but, so it's really, I mean, that's really impressive, Manish. That was really some fantastic stuff. I mean, I was like going, first thing I said was, that's scary. I mean, I was like, 'cause I know Stephen Hawking and a few other smarter people than me had said that, you know, if we're not careful about AI, you know, we gotta be careful what you wish for sometimes, because it, you think about HAL 9000, and, you know, you can think about all the interesting things, but, so what I'd like to do is, I guess I'll just start in this order. I'll ask Varsha from Microsoft to just introduce herself real quick, and then we'll just go from there.
Hello. Hi, everybody. I'm Varsha Raju with Microsoft. I'm part of Microsoft's AI group, and the product that we have, the platform that we have, is called Microsoft Bonsai, which is what Manish was talking about. I am a chemical engineer by background. Most of our team are actually engineers, controls engineers, process engineers, chemies, even a mechanical engineer or two in our Microsoft Bonsai team. So it is an AI technology, but fundamentally it is really about serving specific control and optimization enablement using that technology. And so we have a lot of process engineers and engineers with a capital E in our team, based in San Francisco.
Thank you very much. Prabhu?
Hi, Prabhu Parthasarathy. I'm the VP of Intelligent Operations at Wood. We've been deploying real-time systems. So Bonsai is exciting because we do simulation, real-time systems, a perfect blend of the two. My background is I got a PhD in mechanical engineering, fluid dynamics, thermodynamics, but I'm an honorary chemical engineer because my dad's a chemical engineer, and I've been doing chemical engineering for 20 years. So,
Lisa?
So I'm Lisa Williams from OLI Systems. I've been there for about a year now. I'm, I think, in that one outlier here. So my background is computer information science, and I'm helping OLI come from, the R&D and simulation only area to bringing the simulations out into the operations side. So we've developed the cloud API, and we're breaking those data silos and making those new results available to everybody. And as you've seen from Nicole's presentation, it's got a big impact. So it's a 50-year company that is really getting a larger amount of exposure, because we've always been in the background helping on the thermodynamic simulation. First principles, no training here. It's all science. So, and bringing that out to the operation. So good to be here and see everybody today.
And Sandeep?
Hi, everyone. My name is Sandeep Chandran with Connected Industrials Honeywell. Been with Honeywell 20 years. I'm a chemical engineer by training. At Connected Industrials, we focused on software solutions that enable autonomous, semi-autonomous operations. So there are 4 major pillars there. One is plant-wide optimization, which is the next generation of advanced process control. We focused on asset performance monitoring. We focused on remote operations, demanning platforms, demanning facilities, and finally, sustainable operations, monitoring flares, energy-intensive process operations, fugitive emissions, and so on. Happy to be here.
Great, thanks. All right, we got a pretty good audience, so I'm going to hopefully, I got some questions here, but I want to give the audience an opportunity to, ask their questions, and then we have a mic person back here, so just raise your hand, and then we'll get your questions going. Cavestro, great, thank you. I knew I could count on you for a good question. Thank you.
So I got a question for Varsha, but first a comment for Nicole. I grew up in Sidney, Montana, so I feel your pain.
My newest member lives in Sidney, Montana, and he's the reason why the API was necessary. He was my midnight call.
But Varsha, how big of a model can Bonsai train on now? Like a steady state simulation of an entire processing unit, for example? Can it be that big?
Yeah, we don't think about the constraints of the model in terms of the size, or, is it too complex, too enormous? What we really want to make sure with the model, so the short answer is yes, we can do steady state simulations, we can use dynamic simulations, we can use first principle simulations, so chemistry and physics models. We can use MATLAB, Simulink, ANSYS, so there's lots of third-party models we can use as well, VP-Link. But the key piece that we look for when we're looking at the simulation model that we build for a reinforcement learning application is, does that simulation sufficiently capture the variables that we need to consider and the actions that need to be taken as output? And that's really what we're looking for. Does it sufficiently capture those two things? And if it can, then we're good.
Yeah, just to add to that, I mean, when you're doing any simulation modeling, obviously you're trying to solve a problem, and you've got to take engineering decisions on what is important, what is not important, right? I mean, so for instance, you're doing a dynamic model. Sometimes you don't represent full pipes. You just put something that accounts for the time variable there, right? So you would have to make those judgments in terms of what is the problem you're trying to solve and how do you solve it. That needs to go in.
And feel free, any of the other panelists, if you want to interject some perspectives as a response, jump ball, so to speak.
One more follow-up, just out of curiosity. You train the models by running them, correct? Do you foresee a time where you don't have to do that?
Well, I think for reinforcement learning, conceptually, you'll always need some sort of model in which the agent can learn within. So as a fundamental concept, that's how the mechanism works.
Right, but it's totally predictable what the model outcome's going to be. All the rules, everything you need is described in how the model's going to be.
The PDEs. No,
Right.
so if you look at some of the research that's going on today, and it's hugely sponsored by NVIDIA, there's new, I mean, I worry about this because I think existing engineers cannot take that up, but something called PINNs, which is physics-infused neural networks. It's a huge area of research. It's phenomenal. They've already started representing heat equation, Berger's equation, all sorts of equations with pins. So what they're doing is neural nets already infused with the results of the PDEs that you're trying to solve. It's going to revolutionize, in my opinion, how you build simulation models. So it's going to be 5 to 10 years from now, but it's going to happen.
The other area in research is something called as imitation learning, which is relevant to what you said, where the training happens by watching an expert's actions. So where simulators don't exist, the researchers are thinking, what do we do then? And that's where some of the research I've looked at is to sort of Berkeley doing some research in training a robot to fold laundry. And they are looking at one type of clothing, one way of folding, and there's a video of that, which the agent is learning by watching the video. That's called imitation learning, because a simulator of something like that doesn't exist.
And to be clear, when we use the word simulation, it doesn't have to be a complex, dynamic simulation or first principle sim. I would say for most of our projects that we do, the simulation is what we call a data-driven sim. We take DCS tags, we take Excel spreadsheets, and we build a data model, and that is the simulation. So it doesn't have to be particularly fancy. And the other nice thing about reinforcement learning is you don't need it to be super complex and super specified. You need it to be sufficient, but unlike some very hungry supervised learning models or other machine learning models, where you need maybe a very high data source and data fidelity, even for those of you who are controls engineers, APC engineers, who are comfortable and familiar with model predictive control, you'll know that the underlying models in MPCs need to be of pretty good fidelity for them to be making good control actions and really optimizing that process. You actually don't need that level of fidelity in reinforcement learning models, simulation models. So you've got a degree of flexibility there.
Got another question up here? Yep.
Yeah, Varsha, I think that point made me wonder more about, I want to understand reinforced learning a little bit more here. I guess in my mind right now, it seems to be this way of taking AI, pure black box, to hybrid that with more first principles. And we mentioned multivariable control just now. I did run into this example, Microsoft Bonsai. Someone was doing this balancing the broom exercise.
Yeah, cart pull.
And then when I saw that, I said, wait a minute, I look at this equation. This is basically quadratic dynamic matrix control, and so I was wondering, like, is reinforced learning, applying, I take an equation like that, which is basis my experience as an advanced process control engineer, or can I apply even things like first principle, things like thermodynamics,
Absolutely, yeah.
reaction kinetics, and so on. So this is kind of this hybrid of AI and black box AI and my first principles knowledge. Does that sound right?
Yeah, so a lot of the demonstration you're referring to is called cart pole, and it does capture that motion, that movement in a quadratic form. But to your point, the simulation environment in which a reinforcement agent learning can train can include equations, explicit equations that you may have, but it can also use thermodynamic models, we use computational fluid dynamic models, we can use literally linear equations that may be relevant for that particular part of the process. So we use a combination of those things as needed in order to represent the process that we're trying to optimize.
So I would say, think of it this way, right? So you're basically running millions of simulations and building a multi-parameter correlation. I know she gets angry when I say that, but as an engineer, that's how I look at it, right? So you're running this huge set of simulations. Each parameter, how does it impact the process? In your learning, it could be just steady state or it could be dynamic, but you're essentially learning how does each parameter impact the parameter you're trying to control, building this memory of that and using that in real time. So you moved all the computation from the edge to the cloud a priori, and at the edge, you're just doing a quick search scan through what memory you've built and finding the solution quickly.
So I guess my real question is then, what's the advantage that you see, from traditional APC approach or traditional optimization approach, if you will, with some...
Excellent question. So a couple of very specific advantages you get with deep reinforcement learning. One is that where your MPC or APC systems or even PID systems are not sufficiently controlling and optimizing your process because of a much more highly dynamic system than you've modeled in your existing MPCs, APCs, that's an area to consider reinforcement learning, a very highly dynamic process. So feedstock composition is changing. So if you're in oil and gas, refining, for example, you've got changes in crude slates, you've got changes in crude baskets, maybe you've got a chemicals process where feedstock composition changes over time because of various reasons. That's one that's difficult for typical MPCs, APCs to constantly and consistently control well. Another example of where reinforcement learning would be extremely useful is when you've got multiple competing optimization goals. So we work with customers like Pepsi. Pepsi makes Cheetos, and when they make Cheetos, they use extruders, and they've got trade-offs to make. They've got decisions around how do I maximize yield on this Cheetos process, but how do I make the best Cheeto quality I can? So when you've got a process that has to make real-time trade-offs and short-term trade-offs in service of long-term payoffs and decisions, that's again where reinforcement learning can work really well versus MPC, APC. The other piece, I would say another superpower of DRL is related to sensory input. So unlike APCs, vision systems, vision input, auditory input can be considered by reinforcement learning algorithms. So when an operator says, when we're working with mining companies, I listen for certain sounds on this equipment. And that's how I know to throttle this setting or set point up or down, or I have to override my MPC or APC under certain conditions because it just doesn't work well when I've got slugging or when I've got sort of water entrenchment or I'm hearing a certain sound. Those kind of strategies that your SMEs, your operators, your technicians use today can be incorporated into a reinforcement learning agent very elegantly in a way that you can't with APC, MPC. And the other final piece there is what we call unknown states. And this is where, again, with APC, MPC, you have to be able to explicitly quantify what is happening in my process and explicitly delineate the variable, like moisture. I want you to track moisture as a variable. I want to track, concentrations. With reinforcement learning, you don't need to be explicit about all of those variables. It can learn. That's what Manish was talking about. It learns through trial and error. What are the factors that are important on top of what you've already specified, and can create those correlations when it's trained. So big point I'd want to say is we're not saying you replace PID or MPC or APC with reinforcement learning. That's not the takeaway I want you guys to have. It's about saying where you have those technologies, great, and if they're working great, awesome. Where it's not working well, or where you have further opportunities to optimize your process, that's where you can take a look at reinforcement learning to complement those existing technologies.
It's more of a layered approach to analytics. So, for those of you that had the unknown checked at the beginning, you can start at those lower levels. But no, it's not going to be a throwaway. It'll be able to be incorporated into these newer technologies that are coming online. So make sure you think about that. There's less technical debt today because we're not starting from scratch. We're incorporating all of these things that we're doing, even at the first principle level, where I'm at, up into the AI. I think that's important for everybody to understand as you go through your investments and trying to make sure that you're, getting the right justifications.
Great point. Any other questions to the audience? Raise your hand, you won't be shy. Okay, well,
You had a quick question for Oli and Lisa or Nicole. Nicole, outstanding presentation. Enjoy listening to that. Definitely some unique challenges in your area. But particularly the cloud aspect of it, with your application being cloud-based, it sounded like one of the core challenges for the region was communications. How are you supporting the cloud connectivity in that environment then? I didn't hear how that piece was being addressed. I heard what you're doing with it, but how do you address the connectivity piece?
Did you want to answer that?
Yeah, I can answer that. Luckily, our offices at least all have pretty decent connectivity. So specifically with the cloud that we utilize, our database currently is housed specifically only on our server within our building, just due to security purposes. So as long as somebody is within our facility, then we're able to run the cloud and we're able to connect up through. So it is required that it does actually always have at least some sort of internet connectivity. So as of right now, for us, because we are a very limited staff, we do only run the software whenever somebody is actually within the building that has both access to our database along with the internet connection to be able to get to the cloud and retrieve the results back in that time frame. So from there, once it actually is able to be pushed to Azure, then we're able to use just like a standard web browser. So if somebody theoretically, though, did not have connection to a web browser at that point due to being in the middle of nowhere, at that point, we wouldn't be able to fully utilize the results. So for the most part, as long as there's cell phone reception, everyone's able to work pretty well. But in our remote areas, normally, luckily our engineers have not needed that access, but if they do in that instance, as long as they can make a phone call, then they work with one of us instead. But that's kind of our main point to it is we are still very much restricted to somebody has to be within the office to be able to utilize that due to the restrictions of our area.
Can I have another question on what you talked about? I've done scale analysis myself, so I know how, the data can be, the measured data could be different conditions. You got to check all of these. So there's a lot of quality control of the results that need to be done. Mm-hmm. At the scale that you're looking at, 3,800 samples to be tested, what is your quality control process when you automate the results generation, but how do you then vet the results that come out and say, okay, I've quality controlled it, that I can use it? What do you do there?
So from the original quality control standpoint specifically was testing the original studio that was developed by OLI versus the cloud. From any point past that, it's mostly in our lab to have a certain quality control standpoint. All of the results that we do push through this software are originally from our lab in Williston, so they have to meet the lab's quality standpoints. So it's pretty standard for like in Clearwater analysis, like a 10% cation-anion balance. As long as they meet that point, it will go through. If there's any specialty ones we're looking at and there happens to be something flagged or interesting, then we'll look into it. But for the most part, we've done a couple different runs, even further through, to check the original API versus not only field results, but also the original studio, and everything's matched up for the most part for us. It's a very on-point software, which is not amazing because it keeps telling us that we have problems, but other than that, it's a good time.
Great. I had one more follow-up question also. Manisha, as you're talking through the application here and the future plans for those things, lessons learned, any tips or thoughts on how to further accelerate the learning process or the deployment process for future applications or in other applications they run across that would help get the value to the field faster?
I think the lesson that we learned from our two lessons that we learned from our first use case, this is the second use case, were the simulation was the first, where as Varsha mentioned, the simulator doesn't have to be like a full-fledged reflection of the real environment. And we started, and that works for some use cases. So in the first use case, we started with a Python script model that was our simulator. But the environment was so dynamic that it wasn't well represented in that script. So we had to pause and we had to change to, and sort of get licenses to a third-party simulator effectively that did a much better job of that. So in some use cases, it works if it's just a model, but in some other use cases, it doesn't. So that was like a lesson we learned to understand what type of use cases require a proper simulator and what doesn't. So that was one. And second was, in our first use case, we did not have the data scientist with the appropriate subject matter expertise as well. So I think that's a combination we definitely deliberately wanted to wait for and find the right candidate for. So those are, I think, the two probably the sort of make or break type biggest lessons from that perspective.
Anybody else doesn't have any questions? I want to ask Sandeep a quick question because I was really intrigued by Raid's presentation. And we're looking at that project, Sandeep. Could you just sort of elaborate on what was the justification of the project, and then how did you and Halliburton measure the ROI?
Well, for this particular use case, there was not a lot of justification required. It was essentially translating a manual workflow into a digital workflow. And as it exists today, because of the manual workflow, as Rad explained, the actions are reactive. The data comes in maybe 2 days after the fact, and there's not much you can do with it. So with this, it was more about getting data as close to the events as you can, fixing problems as early as you can. But the big picture here was the integrated workflow from the well to the surface, which needs certain data points, and getting this data in enables that workflow. The side effects of this are justification from a safety point of view. Now you have the what we call the deskless workflows, workers connected, so you can pass on information to them to make ad hoc site asset visits, keep them safe from emissions, environmental or other risks that might happen on the field. So part of it was to bring these remote workforce into the mainstream digital ecosystem that we have. But the big picture is to build some digital twins, build some models that connect the wells to the surface and have all the data available to do that.
Okay, Lisa, Nicole talked a little bit about the OLL cloud, excuse me. And I wanted you to see if you could elaborate that in terms of, what about some of the performance characteristics, scalability, easy use, things like that. If you could elaborate a little bit to help us out to understand.
Sure. So we've taken our classic desktop software and broke them down into individual RESTful APIs as endpoints. So we've got, the engine, which is more of a stream analyzer, corrosion analyzer. So we do scaling and corrosion, ScaleChem, and even our process API. So we've taken our flowsheet ESP and turned that into something that can be run continuously. And just looking at the statistics that come across from our customers, we're seeing, even on the small install, which is, capacity, how many calcs you're running at a single given time, they're running 30,000 calcs at a time in a day, and they're not hitting those limits. It's just a continuous pattern that's happening. So, I feel fairly confident in the things that we've been doing and seeing on our scaling to be able to go up and make that even more. So being able to help learn and feed into those other AIs is very, very interesting to think about with the scale of the cloud APIs. I think the other piece that I get really excited about is thinking about you've got how many years worth of history. So I spent 20 years in nuclear, and I put in a historian in 1999. So I know there's 22 years of data there. I can actually go and reprocess all of that and tell you how much has your, a piece of equipment been exposed to a corrosive environment, or how much scaling has been building up in that piece of equipment, maybe since your last turnaround. So it's not necessarily learning, it's a couple of days to go and run all that data and bring it in and start to be able to make the insights and bring what's the condition of the plant to a more complete picture. So, yeah.
All right, I'll throw it back out to the audience. If anybody's got a question, raise your hand. There's some really great discussion here. Got one right there. If you could just tell us who you are, where you're from. I've said that earlier, but
Andrew Vanderpool, Phoenix Contact. I have a question for Manish. So because machine learning is probabilistic at its core, and you are using it in a kind of safety application, what is the crossover point for when you can trust it? Because even well-trained models can do really weird, unpredictable things that shouldn't have happened.
Yes. So I think the analogy that comes to mind is, so in the, to that point about like weird, unpredictable things, in the, when the competition I mentioned earlier, AlphaGo, which is this ancient Chinese game where it was playing against the world champion, this is like every move is documented and studied by the geeks of the game. And there was this one particular move in game 2 where the commentators, and the first game the computer had lost, and this particular move, the commentators were like, this agent is just stupid. This has never been done before. Ended up winning that game, and that sort of that move is now revered as like, oh wow, this is creative, genius, this computer. So I think in a completely unconstrained environment, sometimes those crazy things might work as well, but in a safety critical environment, you define the envelope of it. So you don't let it go that crazy, right? So you just define the safety envelope, and that's your environment to play in. You can test the boundaries inside a simulator, but in deploying, you always, what I've learned from the SME is that you define that safety envelope and that's it, and we won't go beyond that. And in terms of then operationalizing and the deployment of something like that and gaining trust, we don't know like when we are going to do a full handover and how that trust is going to be established. But I think the current intuition is that we would let the current way of working, where the agent is suggesting to the human and human eventually takes the decision over a period of couple of years at least, establish the points of decisions that have been made, and then take a percentage calculation of how accurate they were over a period of time, and then perhaps put some number around it to base autonomy on. But right now, don't know whether we are going to actually be fully autonomous or not.
I'm going to interject.
Yeah.
So I would add a couple of other things to it, right? So one is, even from the field data, when you're making decisions, there are always going to be anomalies, right? So if you're looking at closed loop control, you do have SIS systems, you have your existing control systems that do put a barrier against those kind of decisions, number one. Number two, when you're looking at SMEs making decisions, you are relying on some of their intuition, subjectivity, when they're looking at data that's outside the bounds of what you've seen. And that intuition can be baked in, but it's part of the design process of the brain. Yes, you may not be able to get everything out of an SME sometimes because it's just intuition. Like when I did some of my PhD simulation work, there were things I could see that I can't explain, but when I see a pattern, I would stop my simulation because I knew it was going to blow up. I would just look at how the data moved on the screen, and I knew it was going to crash. That's intuition, but you'll have to dig into that intuition, get it out of the SME as part of the process as you get more fidelity. But you do rely on your base SIS and control system as well here to provide the guardrails. So, so it's not just it's going to go berserk and take over the world like Skynet did, but maybe someday if we completely rely on it, maybe it will, right?
Just a small question. Do you think that we are going to have like a toolbox for AA that any chemical engineer can use without calling a data scientist?
That was not a planted question.
Holy cow, that's like in our tagline. Yeah, so the Microsoft Bonsai platform it's low code, and it's meant for chemical engineers, mechanical engineers, controls engineers, production schedulers. You know, we have a lot of supply chain and logistics use cases you can use reinforcement learning in. So it's meant for people that are not data scientists, because we recognize that the data science population is growing, but it's a very small percentage of folks who have deep operations and SME knowledge, and folks that really understand the kind of controls and process aspects of the business that they're trying to optimize. So the platform is actually intended for exactly the audience you described. So you don't need to be a data scientist. It's low code. It uses a visual kind of interface as well. So, you know, a gentleman there asked about black box. One of the things that we really want to try to create there in the platform is transparency. So it's not so much of a black box. MPC can be a black box, but a lot of our teams and engineers and technicians have gotten used to it. We're trying to create transparency with the platform, with the visual aspects of it, so that you've got better insight to why the agent is recommending or making the decisions it's making, so that when it is in full control, closed loop control, you've got more understanding around decision making, and you've got engineers actually input into design.
Okay, I just wanted to interject. I had one question that I wanted to ask Sandeep again that I brain dead here. You talked about where we are with the sort of workflow digitization. What's next? What's coming beyond, that area?
Right. I guess if you guys recall Riyad's last slide, which was a subsurface to surface workflow. Now that's the end goal. That's the nirvana of the oil and gas world. Just because the organizational challenges today with most IOCs, you have an upstream organization, a downstream organization with their own objectives, KPIs, own systems. So there is a reservoir system, a well system, and then there are the surface systems. There's absolutely no availability of data across systems. So one of the end goals from this program is working with Halliburton is pulling all the data, the subsurface systems, surface systems into one place where you can run twins. So we have in Honeywell surface digital twins. Halliburton has got the subsurface reservoir models. So how do we run these models end to end to replicate what's happening on the ground? So that's the end state. But all that requires data. So we're starting with the basics. Let's get standard data in. Once we have the data in, the models are a bit more accurate. Users trust the model with the outcomes and advisories. And it's a step towards integrating the workflows across upstream.
All right, since I'm moderating the next session, I'm making a command decision. We're going to take a few more seconds. I want to ask Lisa any final takeaways you want to, and then Prabhu and Varsha. Any final takeaways from that?
I was just going to add on to your end piece there, that trust. I mean, it's huge when our people don't trust what we're giving them as software vendors, providers, solution providers, and being able to say, yeah, I believe in it. And that's one of the things that's core for me. I love all this technology stuff, but if I can't walk the plant floor and help people understand how it's going to benefit them every day, then it's for naught. So that's something that's very near and dear to me. So I like the people aspect of it there. So it would be my final thought is don't forget the little guys out there.
Yeah, so one last thing, there was a question about SMEs, right? How, can engineers build AI? For me, I mean, I give an example, and Jack makes fun of me. I built an AI agent myself in about 3 days. Small problem, but I tried it, and I was able to do it. So it was an interesting thing for me. So, but there is a big gap in upskilling, So we talked about 10,000 data scientists, maybe 100,000 SMEs out there. How do you scale this is going to be the next challenge. So we're working with Microsoft to do that, Center of Excellences, working with clients. But to me, that's an exciting phase because we really want to be able to empower engineers to build this on their own. Because once they build, the question of trust, If they build it, they trust it. If you build it, there's going to be a lot of questions, you know. But we want to empower, you know, engineers to do it and scale it, because if you don't scale it, then, you know, so that's the key.
Raja, any final thoughts?
I want to just mention again where this all starts. It's with Manisha's first slide, which is around value. We don't usually try to say, hey, we've got a technology, let's see where we can stuff it in your system. We really want to start with, what are your optimization goals? What are your control goals? What do you actually want to improve? Is it yield? Is it throughput? Is it quality specs? And you got to start with that kind of guiding light and be really clear on what are the goals you need, what are the KPIs that are associated with those goals, and then you figure out where the technology can support and enable that. It sounds really obvious, but sometimes we can get excited with the shiny new toy. And I know we are a shiny new toy, but we always try to recenter and start with first principles, which is what's your goals and is it of value?
Great. Well, I can't thank you folks for sticking around a few minutes later. I can't thank Manish and Nicole and Raid and the rest of the panelists. I mean, it's been for me, it's been fantastic. And I'm still a little bit nervous about some of this this advanced learning stuff, but that's all right. I'll get over it one of these days. Hopefully by then I'll be dead. Don't have to worry about it. But anyways, because I always wonder, like, where's mankind going to be in 50 years from now? And I always,
Tim, Skynet will send Terminator back to kill you.
Yeah, I know. Yeah, that's right. I'll be time traveling by then, right? Anyways, I want to thank you very much. If you're interested in drones and things like that, I have a session here at 10:30, so feel free to stick around. If you're traveling back today, I hope you have safe travels. And thanks for everyone very much for coming to the ARC Forum, and I hope you get a lot of value out of this session. And again, thanks for speaking.